Hello everyone, I'm very happy to be here for this new Tecnicelpa and CADCIP conference. I'm Florian Gallic and I'm here to present you my work concerning the highlighting of the factors influencing a non-contact infrared temperatures measurement during a paper cutting process. This work has been done in the LGP2 Grenoble with the help of Céline Martin and Raphaël Passas. First of all, as you certainly know, surface treatment by sizing or coating is used increasingly in the manufacturers to improve traditional paper grades as well as new products. In order to do so, different technologies are used in cutting station, as for example, Mayer coating or blade coating. Then, after this operation, the paper is dry in drying cylinders, hot air dryers or infrared dryers. However, it is essential to know the temperatures and moisture content of the paper in order to ensure an optimum drying of the paper from the process point of view, but also the economic one. In order to have information concerning the temperatures, infrared technologies are a good compromise for non-contact temperature measurement. And this technology is used on our laboratory coating pilot from RK Coating. This pilot is a modular apparatus with different technologies for coating station, as a Mayer coating or blade coating. We have also control on the web speeds, but the coating width is fixed. We have here two hot air dryers, which the temperatures could be fixed between 20 and 170 Celsius degrees, and an infrared dryer with a power of 2.5 kilowatts. We also have different control on informations on this pilot. First, we have 4 temperature sensors, control of speed and a measurement of it, 2 optic and 1 infrared camera, a coating bus control, and a web handling system which will be installed soon. This is on this pilot that the study is done. In order to set up a non-contact temperature measurement by infrared sensors. Why will you ask? It's to be certain of the measurements obtained and to optimize the placement of the sensors and the web width. So first of all, we're going to identify the different parameters which can introduce changes in the measurement and master them. We have the measurement angle theta, the measurement distance h, and emissivity epsilon. Then, using image processing, we will analyze the temperature profiles after an infrared dryers and see where the temperature sensor may be placed. So first of all, let's have a bit of a theory. So, in order to have information concerning the temperatures, we're gonna link the infrared radiation with an electrical signal and calculate the temperature of the object. This will follow the Stefan-Boltzmann law. As you can see, it will link 3 things. First, the emissivity of the object, the constant of Stefan-Boltzmann, and the object temperatures. But we also have to take into account the reflected ambient radiation and the infrared sensor's own radiations. This will then give, after calculations, this new formula, which link the object temperatures to the ambient temperatures, the sensor temperatures, the detector signal, the emissivity of the object, and a specific constant of the device. The measurement shape, it's a cone shape, which will evolve when the distance between the sensors and an object will increase or decrease. Then, concerning the highlighting of the parameter influencing the measurement of temperatures, the measurement height, angle, and emissivity will vary between these values. On the test bench with a sliding ear sensor that could go up and down, and that can vary about the angle. About the sensor, it's a micro-epsilon sensor with a measuring range between minus 50 Celsius degree to 600 Celsius degrees, with an accuracy of more or less 1 Celsius degrees. Our paper is a very thin and light paper with an emissivity set to 1.95. Concerning the highlighting of heterogeneous profiles of temperatures in the paper width and search of the better position of the sensors, we're gonna do it on the RK coating palette with an infrared camera and use Fiji software. So here you have the pictures of the coating pilot with a coating station, an infrared dryers, the hot air dryers, and the motorization linked to the winding. This is directly after the infrared dryers that the infrared pictures are taken, and after image processing we will obtain the different temperature profile. So first of all, let's talk about the impact of the measuring height h. So here you have the measured temperatures versus the heating temperatures for different age. Here, theta and emissivity epsilon are fixed. As you can see, when age increase, we have between 20 and 60 Celsius degree, no major difference. However, for temperatures above 60 Celsius degrees, age start to impact more and more the measured. The origin of these variations seems to be the measured surface, which will increase with age increase, and the impact of the ambient temperatures. As you can see, for example, here we have differences of nearly 40 Celsius degrees between heating temperatures and measured temperatures. Concerning the measuring angle, we will have here the same figures as before, but here age and the emissivity are fixed, and only theta will be changed between 0 degrees to 60 degrees. As you can see, when age theta increases, small differences are observed up to 60 Celsius degrees. Nonetheless, above this value, significant differences between the heating temperatures and measured temperatures are observed. In fact, as you can see here, we can have differences between measured temperatures and heating temperatures of 50 Celsius degrees. Please also note that the curve x equal y corresponding to the equality between heating and measured temperatures, and these curves merge with the curve for theta equal to 0. But why these variations? It's a good question, and it seems to be linked to the measurement area shape. When theta equal to 0, we have a disk shape measurement. With radius, we will increase when age increase. However, when theta is different of 0, we will have an elliptic shape of center this black point that will be difference of the paper sample, the center of paper sample, sorry. And we will prove it with calculations, show the evolution of the measuring ellipse surface with the sample distant age and sensor angle. And we show that the ellipse surface will increase when age and theta increase. We'll have the same behavior for the OM distance, which represents the distance between the paper sample centers and the center of the measurement area. And when theta increase, the length between OM increase, and it will have an impact also of age. So measuring age impacts on the large radius of the measuring ellipse. Moreover, the measuring angle theta influences the shape of the measuring area from circle to ellipse, as well as the coordinate of the center of this ellipse. Concerning the emissivity epsilon, we have also an important impact to check. Here the same figures as before, but age and theta are fixed, and the emissivity will be set between 0.1 to 1. As you can see, we can have big differences between heating and measured temperatures. For example, high temperatures. We have nearly differences of 600 Celsius degrees. This is also shown by this table talking about the error or relative error on the measured temperatures in percentage. And as you can see, when the heating temperatures increase and the emissivity decrease, we have an increase of the relative error. In fact, the lower the emissivity, the higher the measured temperatures. From an emissivity set to 1.8, the error is less than 5%. But also, the higher the temperatures rises, the more precise the emissivity setting has to be, otherwise it is out of the manufacturing guaranteed accuracies, which is more or less 1 Celsius degree. Now let's check the inhomogeneous temperatures and sensors position on the paper weights. As I told you before, we took different infrared pictures, and then we will use Fiji software to have the different temperature profiles. This represents this profile. So we have here the position of isotherms when 0 is the exit of the infrared dryers, and here the position on the paper weights. I represent here 4 different isotherms between 85 Celsius degrees to 130 Celsius degrees. First of all, what we can see is that we have a non-flat temperature profile. Now, when we increase the temperatures from 5 meters per minute to 10 and 50 meters per minute, we can see that we have an evolution of the area covered by isotherms. For example, for the isotherms at 85 Celsius degrees, which start here and cover a big area, we can see that this area decreases when the temperatures increase. Moreover, we can also see that the faster, the cooler. In fact, when the temperature increases, the maximum temperatures of the web decrease. And it also seems that there is an importance of sensor placements on the web width. In fact, if you put the sensors here or here, you will not have the same information concerning temperatures. But now, is this variations of temperatures impact on the lectures? In fact, it seems to be yes. When we have different placements for infrared sensors on the web after an infrared dryers and putting two helps, one horizontal and one vertical, and a disk, we don't obtain the same values. For the disk shape and horizontal ellipse, we have an average temperatures of 130 degrees, more or less 9 degrees. This is the standard deviation of the temperatures in the regions of interest. However, for vertical ellipse, we have an average temperatures of 102,008 degrees, more or less 15 degrees. So, statistically talking, we have no big differences. I mean, no differences. But now imagine that the temperatures is read on the sensor by a machine operators. What will happen? In fact, only the mean value will be visible with the sensors, and it will result on an incomplete interpretation of the values. Then maybe the operator will say, okay, now we don't have enough temperatures, we will change the setup. But in fact, it will not be a good decision because we don't have all the information about, for example, the standard deviations. So to conclude these presentations, I will say that care must be taken to ensure the emissivity is correctly adjusted. Here, when the emissivity is between 0.8 and 1, it's acceptable. We have a 2.6 error at 100 Celsius degrees. Concerning the angle of measurement, theta, it must be set equal to 0, more or less 2 degrees, to keep a disc-shaped area. The distance h depends on what must be measured, but the further away you are, the larger the measurement area will be, and will consider temperature's heterogeneity. Third point is the temperature profiles at the exit of the dryers. This is a good element of decision to choose the exact locations of the temperature sensors, but it also helps to understand heterogeneous drying issues on the web width, which could be good important issues for paper drying. So now we have a better management of our pilot thanks to the control of the temperatures, and we are going to study the problem with an additional parameters, water, and coating baths. So I want to thank you for your intentions, and thank you Maxime Terrien and Denis Curtil for their help doing this projects which, as I said, have been done in the LGP2 in Grenoble.
Hello, my name is Joana Curto. I'm from Universidade da Beira Interior, and I will be presenting our approach to study the influence of embossing on 3D structure and key properties of tissue paper. Tissue paper process operations are a challenge for modeling and establishment of correlations from the fiber level to the 3D structure and to obtain predictive capacity for softness, strength, and absorption properties. To overcome this complexity that comes from a multi-input, multi-output optimization problem, we designed and implemented advanced experimental and computational tools that will help to optimize process operations and tissue materials. The first column is dedicated to an innovative laboratory embossing prototype designed to study this operation under uniform laboratory conditions. The first image is a paper embossed in this prototype with a pattern designated by micropattern. The second image represents a liquid droplet spreading in a 3D lattice illustrating the unique information obtained by the optical system. Images 3 and 4 are representative of the computational tools developed and calibrated for tissue paper that have been used in this work. The third indicates that the fibers are modeled according to their dimensions and properties. The last column is for the tissue simulator, a computational tool developed to link the 3D paper structure with the final tissue properties. The conjugation of these experimental and computational tools provides valuable information and predictive capacity with the final goal of process and paper optimization. As we all know, one of the fundamental tissue process operations occurs in the Yankee cylinder. The doctor blade scraps and removes the paper sheet from the Yankee cylinder surface, creating a 3D folding effect. The creping process promotes a change in the fiber direction from the machine direction to the Z direction, which results in the breaking of interfiber bonding, promoting softness and elongation capacity of the paper structure. After creping, the industrial-based tissue papers are subject to converting operations to produce the desired type of tissue paper. One of these operations is the embossing. Here, the surface deformations are obtained by applying localized pressure and patterns to improve, among others, liquid retention, properties, and thickness. In image A, we have an industrial-based paper with creping embossed with the laboratory prototype in which the micro-embossing pattern is visible. If we follow the green arrow here, we have in image B, at the fiber level, a blending of eucalyptus and softwood fibers, that is typical for tissue papers. In C, the topography of the creped paper, and in D, a detail of the concavity resulting from the embossing pattern, and a same image. The furnish effect will be studied, and in the right side we have image B, and a biometry histogram of the reference, a 100% eucalyptus bleach pulp. But as we know, the industrial pulp is made with a mixed blend of softwood pulps and has a certain percentage of an internal recirculation pulp designated as broke. On the left side, image A, we have the industrial paper sample biometry. We can observe that we have fiber lengths bigger than 1.23 millimeters and width bigger than 20 micrometers here, that are indicative of the presence of these softwood fibers. On the right side, we have figure B, the simulation of the reference, the 100% eucalyptus made simulated structure, and on image A, we have simulation of the mixture of the eucalyptus and the softwood fibers. As we know, the absorbency properties can be a differentiating factor for tissue papers. So a unique system has been developed for tissue paper, and a simplified scheme of the liquid droplet prototype is presented here. This system captures the phenomenon of the liquid interaction with the 3D structure with detailed information in space and time for tissue paper, as we can see in these results. The evolution of the liquid droplet spreading over time in samples with and without embossing is presented in this image. The samples complexity goes from the left to the right. The first column is for an isotropic 100% eucalyptus paper, and the second is for the same paper structure embossed with the micro pattern. The middle columns of the image are for the paper structure obtained after disintegration of the industrial-based paper. These are isotropic structures with the same mixture of hardwood and softwood of the industrial-based paper without the creping effect. On the third column is without embossing and the fourth with embossing. And finally, the last two columns are for the industrial tissue samples. Both have been crepped and they have the same mixture of eucalyptus and softwood. Then, this in column 5, the sample is without embossing, and in the last column, the same sample with the embossing pattern. The paper structure and isotropy effect resulting from the crepping operation is visible in the last two columns of this image, where we are obtaining an elliptical shape. The evolution of the spreading area over time is defined by an initial fast kinetics for spreading times below 0.5 seconds, followed by a slower kinetics towards a stabilization value for the spreading area. The effect of the fiber mixture is illustrated when comparing the first two graphics, A and B. The image C illustrates the crepping effect. In this image, we will see in more detail that the absorption properties are modified to the creation of 3D effects on these structures. In the image in the right, we have the crepping lines here in blue. So the crepping lines direction is indicated in blue, and the spreading shape of the droplets reflects the influence of the crepping operation in the structure. In these images, the bigger axis of the elliptical spreading area is located along the crepping lines direction, indicating that the crepping has an influence on the tissue paper structure and consequently in the water spreading anisotropy. In the image on the left, here, the embossing micro pattern dots are signalized in blue, and it's visible that the flow, the spreading, is changed by the influence of these topographic effects. When the time progresses, we can see here that for 3 seconds, for the time of 3 seconds, there is the spreading irregularities provoked by the dots, and the liquid goes around and into the valley effect, the concavity effect made by these dots. Let's analyze these clamp capillarity properties from the bottom to the top. The embossing micropattern, the first line is industrial tissue paper. Is a crepped paper that benefits from the micro-embossing, as the red line above this line demonstrates. The same phenomenon happens to the isotropic paper without crepping, the gray line without embossing, and the orange line with embossing. And for the 100% eucalyptus structures, the light blue and the green being the best value for the embossed structure. The tissue simulator was used to obtain the separation of effects, the fiber composition effect, and the crepping and embossing influence, as it is visible in the scenarios and the that are presented in these images in the form of graphics with the positive and the negative influence. The embossing has a negative influence on the tensile index that comes because of the fiber and structure deformations induced by the applied pressure of this operation. The modification of the structures in the Z direction increases the DS7 parameter and consequently decreases the hand field softness parameter. Globally, the embossing operation has a negative impact on mechanical properties and softness, and on the other hand, increases the thickness in the Z direction and consequently increases the bulk. The creped paper presents a slightly gain in the softness property when comparing with end sheets with identical fiber mixture composition. End sheets with 100% eucalyptus present higher softness than similar structure with a fiber composition made from a blend of hardwood and softwood fibers. And to conclude, the methodology presented in this work proved the effectiveness of the embossing prototype associated with an optical system and a tissue simulator to predict the positive and negative trends on softness, strength, and absorbency properties. We'd like to thank the Impactus project, Fiber Intec Research Unit, and in a personal note, Dr. Portugal, my PhD advisor from University of Coimbra, for his guidance in computational modeling and optimization, and for your kind attention. Nosso muito obrigada, muitas gracias, thank you very much. I will be available for questions and discussion, and I would like to thank the authors, the co-authors of this work, a dream team of excellence that made this possible.
Hello, my name is Ana Margarida Carta, and I'll be presenting the work Eucalyptus bark pulp, an alternative source of cellulosic fibers for tissue paper production. I'll start with a brief introduction, and I'll talk about the methods, results, and the conclusions. As we know, the increasing consumer environmental awareness has been driving the demand for more sustainable and environmentally friendly products such as tissue products. And to do this, to ensure new products, companies have been looking for different strategies that, for example, include process optimization or the use of alternative raw materials. If you look at these strategies and if you look at the pulp mill, bark is a major byproduct that is usually burned for energy in vapor production. However, this is still a lignocellulosic material that could be further exploited for pulp and paper production. However, bark pulping is not an efficient process due to its composition, that it's rich in extractives. And many strategies have been developed over the year to valorize bark, but looking at the point of view of extraction of extractives and valorization of extractives. However, little is found regarding the use and exploitation of the resultant lignocellulosic material for papermaking purposes. With this in mind, the main purpose and aims of this work were to evaluate the properties of bark pulp resultant from a pre-extraction process and a kraft pulping process, and to evaluate the potential of this pulp as an alternative raw material to be incorporated in the production of tissue papers. For this study, we used eucalyptus bark from a mill, and this bark was initially subjected to a pre-extraction process with a mixture of ethanol water, and then after this process of extraction, the bark was subjected to kraft pulping in a laboratory reactor, and then the resultant unbleached bark pulp had a kappa number of 13.9. This pulp was then used to the other study. In the following studies regarding papermaking properties, unbleached bark pulp was characterized for chemical and biometric parameters alongside with two commercial pulps, a bleached softwood kraft pulp and a bleached eucalyptus kraft pulp typically used in tissue paper production. These three pulps were then used in different formulations to evaluate the effect of the incorporation of bark pulp in typical tissue paper furnish mixtures. To do this, we considered a reference mixture of softwood and eucalyptus pulp, and then two other formulations where we substituted the eucalyptus pulp for bark pulp in 20% and in 30%. With these formulations, we prepared tissue laboratory handsheets, also typical ISO standard handsheets. And these sheets were then analyzed for its papermaking properties. Considering the results, if you look at the biometric properties, we see that softwood pulp and commercial eucalyptus pulp had typical values. Now looking at the bark pulp that we produced at laboratory scale, we saw that this pulp had similar morphological features to that of eucalyptus pulp, which was expected. Also, this bark pulp fibers also revealed higher coarseness values, which could be ascribed to the fact that the pulp was not bleached, did not suffer further processing. Also, this higher coarseness could be interesting because it's relatable with bulkier papers structures. As regards the chemical and structural properties, it was found that softwoods and eucalyptus commercial pulps had typical values. Now looking at the bark pulp that we produced, it revealed a higher intrinsic viscosity when compared with eucalyptus pulp, which was attributed to the fact that it was unbleached pulp. Also, this pulp also revealed a higher carboxyl content when compared with the backpack, and also it revealed a slightly lower value of pentosans and extractives, which was relatable with the fact that we used a pre-extraction process for its production that removed most of the extractives alongside with some sugars. Afterwards, the bark pulp produced, as I mentioned before, was used to prepare different formulations, and these formulations were used to prepare laboratory tissue handsheets. The results of the analysis of the tissue handsheets revealed that the incorporation of bark pulp yielded an increase on bulk, an increase on water absorption capacity, and also an increase of air permeability. And this result was attributed to the fact that we are incorporating fibers with higher coarseness in the furnish, so it results in a fiber network with more void spaces for water accommodation in case of water absorption and for air passage in case of the results of air permeability. As regards tensile strength, tensile index, it was found an increase, and this increase in strength was attributed to the fact that we are incorporating fibers with higher intrinsic viscosity and thus higher intrinsic strength. In case of softness, this parameter was analyzed for all formulations and no significant variations were found. To further complete this work, we prepared also typical ISO standard handsheets, and we found that the analysis of these sheets revealed similar trends to the results we found on the laboratory tissue handsheets. So the incorporation of bark resulted again in an increase of bulk and capillary rise. And in case of Gurley air resistance, lower values, which are attributed to the fact that we are incorporating once more fibers with higher coarseness that favor the formation of a network more more void spaces. As regards strength properties, we found that tensile increased alongside tear index, and these results were ascribed to the fact that we are incorporating fibers with higher intrinsic viscosity and thus higher intrinsic strength. In case of burst resistance, we found some little variations, and this was explained by the fact that this property may not be as affected by intrinsic strength variations as tear and tensile. As regards opacity, the incorporation of bark pulp resulted in a sheet with higher opacity, also with some slightly creamed color. In conclusion of this work, we found that the pre-extraction process and kraft pulping of bark resulted in fibers with similarities in case of biometric properties to those of eucalyptus wood, and also similarities between chemical properties of bark pulp and eucalyptus pulp. Also, we found that the incorporation of bark pulp in typical tissue paper furnish mixtures resulted in an enhancement of key tissue paper properties such as bulk, absorption, and strength properties with no significant variations of softness. Thus, in light of this, we see that bark pulp could be a potential raw material to be incorporated in the production of tissue papers for the development of a new concept of products more ecological and sustainable. I'd like to thank you for your attention. This work was carried out under Project Impactus and co-financed by Compet and Portugal 2020.
Thank you, Mr. Chairman. It's a big pleasure for me to be able to present from my house in Stockholm, and despite the actual situation, part of our studies on improving the strength by proper process water management. It will be precisely on this process water management where we will put the focus of this presentation, as we consider that it has to be given the importance that it has towards optimizing any kind of processes. Today we would like explaining first of all what is today's situation when it comes to packaging grade. In the last years, there has been a slow increase in the sales and the needs of packaging grades. However, if we see at the production figures, there has been a clear increase in production capacity that creates a challenging situation for the different suppliers, where there is a need of a clearing. In a challenging market, there will be two possibilities. Either increase the product quality to reach other markets, or reducing the production cost. If we focus a bit more in liner and flatting production, we will speak about increasing the product compression, the bending stiffness, or reducing the specific grammage to get the same strength properties but with higher speed. What it will be required is a better performance in the production line. And we will show what is needed to that. What we see now in the screen is what happens many times when a mill starts to increase the strength. What we will see many times is a reduction in the dewatering, as we could see in the water line on the wire, and a higher difficulty to remove this water afterwards in the press. In this case, if we see Molino graph, we will see that despite a potential increase of up to 20% of the strength, the water line was moved towards the end by more than 20%, and also the dryness before the size press was also reduced. We reach from 3 to 8% in water content. That will mean that if our machinery, our chemicals are not able to cope with that, we will be able to reduce the speed of the paper machine if we would like to get this strength. So how can we, therefore, increase this strength without affecting negatively the economy of the process? So first of all, if we want to increase the strength, we will need to work in two areas. We will need a better dewatering, and we will need to improve the bonding ability. If we want to have better dewatering, we will need to have a better flocculation, and also both the flocculation and the improved bonding ability will be deeply linked with a better chemical efficiency. And if we want to have a better chemical efficiency, we will need to work on improving the process water. But that's not only that. If we improve the process water and we get better chemical efficiency, we would be able to deliver chemical savings, and through a better dewatering, we can also get energy savings. So it will be up to every company to find the better optimum use of the different resources. So if we go a bit deeper into how is linked this process water in the strength and in the flocculation, what we have been doing, so using, we could say, quite traditional systems, but also we have added the focus beam reflectance measurement, which will give us an idea and a way to follow the size of the flux and therefore be able to optimize. When it comes to simulate the paper machine at lab scale, we have used different tools depending on what we want to improve, because it's very important that when we try to optimize the dewatering, we are considering what is happening in the different parts of the process. So as an example of the link between the process water and this chemical efficiency, we could show two examples in the screen. On the left side, what we see is the evolution of the particle size at different levels of conductivity when we dose given amounts of cationic starch. What we could see, so the grain line will be with a low conductivity, and as we increase the conductivity, we see that the flocculation effect of the starch is disappearing completely. On the right side, we could see what will be the impact on the strength, and what we saw is that when the conductivity on the waters was higher for the same amount of cationic starch, we lost about 6 percentage points on the strength increase. But we consider, okay, how can we handle this conductivity? On the other side, we have to consider also the importance of the cationic demand, the importance of the anionic trash in the system. So now what we see in the graph is the evolution of the theta potential, therefore the charge on the fibers, with the addition of different amounts of cationic starch. And we see two curves. The blue curve corresponds to a pulp without the addition of any fixative, so therefore without any control of the cationic demand. The green curve will be the same curve, but when a fixative has been added to the process. What we could see is that to reach the same theta potential, we can reduce the dose by about 60%. And even if we include the cost of the fixative, in overall, it will be a 23% cost reduction. But if we look at this graph in another way, and we consider that normally the amount of starch that we can produce and that we can add in our machines is limited, it will mean that if we are not working with the cationic demand, we will not be able to reach a neutral enough theta potential to really develop all the strength that the system can give. Another way that we have used to follow and what we said to improve the quality and the dewatering is with the EBRM tool. What we see now on the screen is the evolution and the relationship between the cord length, that is the particle size, and the dryness before press on our pilot paper machine in Stockholm. On the right side, what we see is the evolution during time of this average particle size. And what we could see is that there is quite a clear relationship between the particle size and the dewatering. that will allow us to follow and to optimize the system continuously. With these ideas, we started a project funded by the UK Department for Business, Energy and Industrial Strategy, together with the company TSMIS, to see how we could improve the dewatering in the machines and reduce energy costs. When we want to consider what is the impact of the different components in the system, it's very important to understand where are those contaminants coming from. They can come from the pulp, they can come from the water that comes with this pulp. We can be adding them with different chemical additives. It can come with the addition of fillers. It can come with raw water. But something that is very important is that there could be different transformations that happen in the process. And another thing that is very important is that there is a cumulative effect on the composition and the concentration of these contaminants. That means that when we reduce the water consumption, we will be on an exponential situation where any small change will have a dramatic effect on the composition, and therefore a dramatic effect on the efficiency of the chemical. So what we did in that project was to evaluate the system, to evaluate the different streams that were reaching the paper machine, and understand how we could improve the system. We saw 4 different action points. We could improve the behavior of the thickener, the last thickening stage after the pulp line. We could improve the use of polymer on the sable unit. We could also fix or try to fix the remaining cationic demand to the pulp. And we had, of course, to optimize. Once we had changed the characteristics of the pulp and the water, we had to re-optimize the retention system. And that was the objective of the project. So even if we will not go to all the details on the results, we wanted to highlight some of the results. Probably the most important result is what we see now on the screen. So by handling the system properly and fixing the cationic demand, we managed to see a 10% reduction in steam consumption. We also worked the same that we have done on the pilot machine with the ABRM, with the possibility to install this online. And what we see now on the screen is a relationship that we had at the mill between the dosage of chemicals, the data from the ABRM, and the couch vacuum, and therefore the dewatering at the end of the water. And we could see that there was quite a good relationship that allowed us, using the ABRM, to have a continuous optimization. Summarizing the results of all the project, what I said, so I cannot go into detail of all the results, but we managed through this system to, by adding the polymer in the thickener, we saw a 40% reduction in the filtrates. We managed to reduce even the consistency of the white waters of the paper machine, and a 15% reduction on the polymer to the sable. In addition to that, working with this polymer, we managed to reduce up to 28% reduction with a positive impact on the wet end control. We optimized the dose of fixative to the blend test, and we saw this 10% reduction of steam with a 27% reduction in cationic demand. And also, when we work with the retention system, we saw that even if the bentonite was limited, on the sense that over a given level we were not able to improve more the dewatering, by the addition of other polymers, we saw that we could even improve better the dewatering. So, concluding my presentation, what I would like to keep in mind is that, so if we want to increase the strength, we require improving the dewatering in the paper machines. This dewatering is normally limited, both from mechanical side, but also by the efficiency of the chemical systems used. So we will need to work on the process water and control the contaminants reaching the paper machine. And what we saw is with the proper process water control, we can deliver energy savings, we can reduce the chemical consumption, we will have a better control on the system, and what is more important, and summarizes the objective of this presentation, is that it will open the door to different improvements on the product quality. So therefore, what I would like to leave as a learning out of this project is that when we handle the process water properly, we will be opening also the door to future product quality improvements. Thank you very much for your time and participation, and I am open for any questions that could come. Thank you.
Sorry, I was without sound. I want to thank all the speakers for these very good presentations. My name is Paulo Ferreira. I am a member of Tecnicelpa board, a professor at UC, and also a member of the organizing committee of this conference. We have here some questions for this period of Q&A. I will begin by a question to Florian. Can you all hear me?
Yes.
Yes.
Okay.
Hello.
So, Florian, can the IR sensor be used to monitor and control roll temperature in other stages, for instance, paper calendaring and after coating?
Well, yes, but we have to be careful of different aspects. Concerning monitoring of the roll in paper calendaring, you have to first know the emissivity of the material of your roll. So it is very important. Maybe you during my presentation you saw that the emissivity is really a key point for the temperature measurement. In fact, you have to take the emissivity, but also the geometry of the surface. So in the case of the wall, you will not have a perfectly flat surface, so you have to be careful of this too. You have also to be aware of the impact of the surface roughness of your materials. In fact, with metal, if it's oxidized, polish, etc., you will not have the same behavior and the same information provided by your sensor. So this is for the monitoring. So I would say yes, but you will have to be very careful of the different parameters you want to enter in your sensors. And concerning the control, with this kind of device, it is possible to obtain an electrical signal as an output between 0 and 5 volt, for example, or 4 and 20 milliamperes, so that it helps you to first monitoring with Python code, for example, but also with, for example, a national instrument device for data acquisition to use this electrical signal and send it to PID controllers. So maybe with this kind of systems and the proper device, you can also create a control. So you can, I don't know, fix temperatures for your calendaring roll. Then with the sensors, obtain the electrical signal, send it to the PID controllers. PID controllers check the information compared to the value you wanted, and then change the value in the roll calendaring. So yes, the roll calendars if necessary.
Thank you, Florian. Before proceeding, I would like to ask our participants who put some questions that if they are not, if they want to go deeper in some clarification or explanation, please go again to the chat and make again another question. Now to Joana, how do you use your computational approach? Can you explain further?
The computational approach is used to link the 3D fiber model to the structure made from these fibers and to have a similar structure that the one that is in paper. And so to change the parameters of fibers and using this computational simulation. This is always validated with experimental data. And then after this validation and calibration, we are able to predict if we change a percentage of a fiber, for instance, an hardwood fiber, or the percentage of the the fine components in the mixture. And also we use computational tools to separate effects. Creping and embossing go together in the industrial process. And then if we separate these using computational tools, we are able to predict trends of each of the operations. What if we do directly in the industry, it will be complicated because everything is mixed in the paper. With this strategy, we were able to separate these effects and the influence in the paper properties.
Thank you, Joana. Now I think we have a question to Anna. Yes, Anna. Is this approach economically viable? And what do you think about reducing the percentage of softwoods and increasing the bark pulp incorporation?
Regarding the economical viability of the process, this process is being evaluated at RAIZ for other applications for biorefinery. They are looking to try to valorize extractives and the bark pulp. So I took, with collaboration with my colleagues, we decided that what if we use further exploited this pulp to paper? So it's a question that for now we are analyzing. It's an economical viability that is being analyzed for biorefinery alongside with this project. So for now, I don't have data. It's something that is under analysis. Regarding the percentage of softwoods, yes, since the incorporation of bark pulp resulted in increasing strength, it's possible that it allows some space to remove and decrease the percentage of softwoods. We didn't test it at these trials, but it could be something to try.
Thank you, Anna. Actually, I had here the same questions, if this pulp could be used to other paper grades. Well, but I will go into this later after the questions of the audience. Now we have a question to Ignacio. Yes, the fixative you mentioned is a typical anionic trash catcher, or its aim is to fix cationic starch. You want me to repeat the question?
No, I understood. So it's a good question because, by the way, it was not a traditional anionic trash catcher. It was, by the way, what we call a hybrid fixative. And the question is quite good because it was seen that it was needed to add a given amount in order to have an effect. So with a lower amount, it was not possible. And using this hybrid fixative with also an kind of a flocculation effect is where we managed to have this effect. But the aim was not to fix the cationic starch. The aim was mostly to try to fix and reduce this cationic demand. So not only coming from the starch. We were not aiming especially to fix the cationic starch.
Okay. I think I went through all questions. Just let me know if I did it. To Florian, to Ignacio. This one is to Anna again. The combination of high bulk and strength is interesting. Do you anticipate good applications in packaging or even copy paper?
It could be interesting for packaging because packaging requires higher tensile and in some cases tear. And in the typical ISO standard sheet for the tested mixtures, we saw that. So it fills in the requirements. So it could be an option. Yes.
Okay. We have another question to Ignacio. Is it possible to have the same approach for fine paper processes and, more specific, if we can get better internal bonding and, as a consequence, less probability to have delamination problems in the gap former.
Thank you for the question. The answer, I would say, is yes, but because what we are doing is somehow to give the process chemicals to do their work, on the sense that nowadays, and how I would say a bit unfortunately papermaking has worked, has been like letting the process water to cope with whatever we were adding to the system and then adapting the chemicals to that process water. What we are trying is to revert this on the sense of we clean the process water, and then, so the idea is that each chemical then will be able to produce the effect that is supposed. So the same that for internal bonding. So at the end, all those chemicals, they are a bit looking for similar functions on the sense of binding with the fiber. If this fiber is not accessible, and even because we have just linked to this fiber a lot of the trash in the system, so it's a bit this change of mind, and then its process will require a specific action. But the fact of, for example, implementing the FBRM or any technology to follow the population will help a lot to optimize also this internal bonding.
Okay, thank you, Ignacio. While we wait for some more questions from the audience, we don't have any more by the moment. I have here some questions also for you. First, beginning by Florian. Do you think that it is easy to get the emissivity values since they are quite variable and they affect the results of your measurements?
Well, this is not that easy, in fact, yes. As you say, it is quite variable, and we admit that we have an acceptable error on it. So it's quite complicated to have perfect values. But when we check for different emissivity parameter, we obtain, as I say, an acceptable relative error. The main complications came when we start to coat the paper with the humidity that impacts the emissivity. So as I said in my presentation, this is the next step we want to check. And because with the thin layer of water on the paper, it would totally change the material. We start with paper, then we have coated paper, an undried coated paper, then a dried coated paper. So this different stage could lead to different emissivity to find and to set up in the parameter of our sensors.
Which temperature do you use for coating?
For the drying, you mean?
No, in the formulation. What is the temperature?
Temperatures for the moment we are between 30 and 40 Celsius degrees, because if we go further we start to have evaporation of water, and then we don't have the same, of course, viscosity, the same properties, and it change then the result.
Besides the results you presented reveal that the method after 60 degrees has bigger errors.
Yeah. So for the coating, as I said, this is so you ask for the temperatures of the coating bath, but after for the drying temperatures, we go further. For the infrared dryer, we are up to 130, 40 Celsius degrees, and for the hot air dryers, we are for nearly 150 Celsius degrees.
But these ranges, you have some measurement errors, don't you?
Yes, we have. Yeah, we have some. Yeah.
Yes, that's the point. Well, we have here another question. I suppose, yes, it is for Anna. Have you evaluated the removal of inorganics from the bark in the pre-treatment, especially because of the risk of greater incrustations in digester and evaporators?
I need to check that. I believe because this part of the cooking with the pulp was mostly done by my co-authors, Pedro and Ricardo. they were the one with the part of the cooking, and I believe they've analyzed that, but I need to check the data. I cannot tell you exactly they've analyzed that, but I think they did, but I need to check on them.
Okay. Joana, well, I was particularly touched by our tribute to Dr. Portugal, who passed away prematurely last January. We miss him a lot. I have a question for you. Your simulator was developed according to the embossing pattern you have built up at UB, at your university. Is it? Did you validate it to other patterns? Do you intend to do it? Do you think it is valid for other patterns as it is?
Yes, the work was the experimental plan was done with two patterns, the micro and the echo pattern. This is with our the co-authors. Joana Vieira is doing his PhD in embossing, and for this part, Tecnicelpa, we presented only one pattern, micro pattern. We chose to present only one, but we have done the experimental part simultaneously, and because the pattern is a flower, something bigger, the results came very interesting, and we have been analyzing them. So this is one of the things that the simulator also can compare, if several patterns and also the conditions made in the embossing prototype that was also developed in University of Beira Interior. And I would like to say that the part of the modeling of the fiber and the structure was developed in my PhD with Dr. Portugal and Dr. Eduardo Conceição. And not only when I was writing it, because it was everything came to my memory, the supervising and everything I've learned with them, and also with my professors, which I would like to include you, as you know, from COIMBRA. This was an opportunity for all of us to be in COIMBRA if we were not in this situation, and that was something all of us wanted to do. The former students, the current students, but the spirit is there. The things we learn, the things we teach, I think will stay with us forever. And one of the things that I was always thinking when I was writing and presenting is what it was the gratitude for everything I've learned in this way. And the computational simulation, it's not an easy tool to be working with and to prove that is effective to predict paper properties, but without this way, this path, I wouldn't be here. So not only to the co-authors, this is a work where Tissue 1 and Tissue 4 from Impactus, which is guided also by Anna, that is here. That's a work that we have been doing in the past 2 years with a lot of enthusiasm, good results. And in this work, a prototype for embossing, a laboratory prototype that allow us to do this operation in the lab in an uniform controlled way, and also an optical system developed by Antonio and Paulo Ferreira, which is able to we are able to see the spreading of the in a paper that is so different from the printing paper, low grammage, big porosity, fibers that give smoothness. Everything is different in tissue paper. One of the things that we all share, Ana Paula, Emilia, Rogério, all the authors, is the enthusiasm for being able to apply our knowledge. Our PhDs were in paper, as yours, but now it's tissue paper. Everything is challenging, and this has been a very interesting path, and a lot of challenges are still ahead of us. But this strategy to have good prototypes that are unique and calibrated for this kind of paper, the embossing prototype, the optical prototype, give us valuable experimental information. And also the computational tools give us capacity to predict, to see what happens if we change the composition of the hardwood that we know that is changing, or the fiber flexibility that changes when we change beating of this fiber. So we have a lot of potential here. We are looking forward to continue this work. And I think with this work is the best tribute I could give to Dr. Portugal. In our last meetings, I was able to show him the tissue simulator, and also the use of the voxel simulator that was developed by Eduardo Conceição in my PhD. So we could have a meeting where he was very enthusiastic about being able that the PhD that was done 10 years ago or was still giving fruits, and he was still giving ideas for the optimization. So one of the things that gave me great pleasure in the last, when it was already here, but it was the same enthusiasm that you could see in my PhD. And so one of the things that I could see is that, we are continuing the works of others. I'm feeling like I'm continuing not only my work, but his work, Eduardo Conceição work, my professors, and also the colleagues with the ones I work now, with these challenges of tissue, what we didn't know anything about when we began. And now it's so interesting to be able to use these tools. These tools can also be applied to other kind of papers, in tissue. There is a lot of kind of tissue papers. So our future challenges will be to apply this to toilet paper, kitchen paper, special tissue papers. So there is a lot of work to be done that we are eager to continue. And I will thank you.
Thank you.
Okay.
I had here some more questions, including Joana, but they put me a timer here in the screen. I'm afraid they will cut the session, but I will try to make this one before. Did you make any biometric analysis of the bark fibers before pulping?
No, we analyzed after pulping, because before pulping, we didn't segregate or take lamellas from the bark to analyze on microscope. And we just analyzed on a fiber tester.
Yes, sorry? And pulping was performed according to the hardwood conditions.
Yes. The pulping, the craft pulping was according with the conditions shared on the presentation.
Yes, those which are similar to those of hardwood fibers. Yes. The point is that the bark morphology after pulping seems so similar to the one of hardwoods that I'm afraid that it can't, it would not be as adequate as that to replace the softwoods, because actually it is much more similar to hard than to softwoods.
Yes, that's why we on the studies went for the strategy to replace eucalyptus for bark.
Yes, your presentation was very clear. Thank you. Ignacio, I was also always a bit concerned with the fact that to study flocculation in lab, we need 30 minutes, 20 minutes, 15 minutes for the flocks to be formed. And actually, at the paper mill, we don't have that time. Can you talk about this?
No, so when it's about, I would say the flocculation is quite fast on the sense, and that's why we need this good enough control. We need to be able to follow it online, and so what we see, and at the end also, and there has been many studies. So one of the typical mistakes when we try to study flocculation is think on the flocks that are formed, not on the flocks that will remain after the head box. So even
yes, but at the lab, we need much more time to see the flux formulation, isn't it?
But not say that's our experience when we use the FBRM methodology. It's quite so. If you see the length of the experiment, we get quite a good evolution in an issue of minutes. So it's more I would say the degree of mixing you get.
The minutes is a lot. Well, we can continue later, maybe out of this session, because I was informed that I have to finish. So thank you again for all your presentations. It was a very good session, and I wish you all the best. And thank you also for the participants who made questions at this Q&A session. Thank you, and see you soon.
Thanks to you.
Thank you.
Thank you.
See you soon. Stay safe.